Hello, today I'll be talking about one of the most common tools in classification called logistic regression. So let's start with what we discussed in the previous video about linear regression. Linear regression is supposed to be used for a task called regression. And in regression, we are trying to predict any real number. So it can be negative 165, positive 144, or anything really, any real number, and it's a continuous value in this case. In classification, on the other hand, we are trying to sort of classify certain data points into classes. So we need discrete class labels. We can't have class 4.5 or class 4.6. We have to have either class 0, which represents no, class 1, which represents yes. That's in the binary classification case. Some common tasks as a recap for classification include spam filters, because we're trying to classify emails into spam and no spam, or animal classification like mammals or amphibians, etc. But we also need a probability, and it's basically the probability of that the specific data point landing in that class, in which the highest probability determines the which class it actually goes in. Linear regression can't be used for classification because obviously it outputs any real number, but we need discrete class labels. So we need to sort of, we can't just have linear regression do that. So instead, we can convert this regression problem into a classification problem by using a very special function called the sigmoid function. And basically what it does is it squashes that range of real numbers, for instance, 1444, or any number, into the range 0 and 1, where 0 represents no and 1 represents yes. Of course, this represents the sort of the binary classification tasks, just for simplicity. So if we get it somehow into this range, then we can make operations on it that are suited for classification tasks. Then we can actually classify it into 0 and 1, unlike if we have the whole real number range, right? The function that does this is the formula below, which is called sigmoid. 1 over 1 plus e to the power of negative z, where z is like a linear model, for instance. So then what's logistic regression? In contrast to its name, it's actually not a regression model, as we discussed. It's used for classification. The first step, however, defining z, is the exact same as defining a linear regression model. We just have a weighted sum of the weights with the inputs and then add that with the bias. So it's basically just a linear regression problem from step 1. But what logistic regression does to convert it into a classification problem is it then uses that function we discussed, the sigmoid, to convert that into sort of discrete, or probabilities actually, between the range 0 and 1, which we can then use for binary classification, where 0 is the one class and 1 is another class. So it sort of converts that into something we can use for classification. Here's the trick that makes logistic regression work. We discussed how when we use logistic regression, the sigmoid squashes these values into any value between 0 and 1. So what do these actually represent? Well, we can see them as probabilities, right? Because probabilities, after all, they are also between 0 and 1. And so we can see this as the probability of a specific class. For instance, let's say 0 was like not spam, and then class 1 was spam. If the output is greater than 0.5, for instance, if it's 0.7, 0.9, then it's closer to the class 1, so we can just classify that as spam. Meanwhile, if it's less than 0.5, we can just choose not spam, right? Because it's closer to that one. There's also confidence in this, in the sense that our probabilities don't just represent don't just tell us which class to classify into, but also a measure of how confident the model is. If we say that class 1 has a 0.95 probability, for instance, then we're significantly more confident than if we say class 1 has a 0.85 probability. So we can see that this sigmoid sort of encodes both confidence and probability. Likewise, for class 0, 0.15 is more confident than 0.25. So basically, the more away from the middle point 0.5 is, the more confident it is, because 0.5 is like the decision boundary. So let's investigate this even more. What is a decision boundary? Let's start with that border, like the right in the middle of two decisions, class 0 and class 1. At this point, we're maximally indecisive. Because we're in the middle point, we're not strongly uh, aligned towards one specific decision. We're right on the fence. Interesting enough, this implies that Z, the input to the sigmoid, is 0. And if we go back to here, if Z is 0, then this linear regression part must also be 0, right? Which is basically just the dot product between the weight vector and input vector. And we're letting that be 0. If it was discussed in the previous video. If the dot product is 0, then the weight vector is perpendicular to the input vector as we discussed. This means that when the weight vector is orthogonal or perpendicular to the input vector, then we are at a decision boundary, or like on the fence at the very border of two decisions. And in that case, we have maximum entropy, right? Which is just a fancy way of saying like how uncertain you are or how much chaos is in the system. So we are maximally uncertain at this decision boundary, and it all makes sense. But what can we say about the gradient or derivative of sigmoid? Let's walk through this step by step. First, start with the definition of sigmoid, which we can rearrange as 1 plus e to the power of negative z, or that to the power of negative 1. Because we can just rewrite that fraction as that form for basic algebra. Let u be 1 plus e to the power of negative z, so that's like the inner function, right? Then finding the derivative is just applying this chain rule, where 1 plus e to the power of negative z is the inner function, and then u to the power of negative 1 is the outer function. So this is sort of like a composition of two functions here. Per the chain rule, we can then differentiate the inner function and the outer function and multiply them together. So the outer function's derivative is, we use the power rule here. We bring down that exponent and then subtract it. So it's negative 1 plus e to the power of negative z, or that to the power of negative 2. So that's the outer function derivative with respect to u. The inner function, 1 plus e to the power of negative z, is the derivative of that is negative e to the power of negative z. And now we just multiply that by the other one. Notice here that there's two negatives. So in the first term, there's negative. In the second term, there's negative in the negative e to the power of negative z part. Well, then we can just cancel them out because there's two negatives. So we get 1 plus e to the power of negative z, or that to the power of negative 2, times e to the power of negative z. And because we can use the index laws again for algebra, you can see the negative 2 on the top of the first term. That's just basically the same as if we write it as a fraction, e to the power of negative z divided by 1 plus e to the power of negative z squared. So we just use that rule. And here's where it gets really interesting. If we can split this into two different fractions, because there's like a square in the middle, it's just 1 plus e to the power of negative z times itself, then we can rewrite it equivalently as the fraction below. And if you notice, the second term, 1 over 1 plus e to the power of negative z, that's exactly the derivative, that's exactly the sigmoid function itself. And then the left one, the first term, that's just 1 minus that function itself. So after all this, while the derivative this is true, it simplifies beautifully into itself times its complement. So the derivative of sigmoid is actually very elegant. It's just itself times 1 minus itself, so basically its complement. So now that we've got this simple, elegant formula, how do we connect this to the Bernoulli variance? Well, it turns out they are the same formula, which means we can sort of find like a relationship between them. There's also social welfare to consider, and this one's a bit more researchy, but we can sort of think about it in that way because this connects to, once again, like the product models in social sciences and decision theory, which is like multi-attribute multiplicative utility. And in this case, we can see that this as like controlling a budget or resource allocation in a way. Imagine you wanted to divide one, where one is like the total quantity between like two people, right? Then sigmoid's derivative encourages fairness and sharing resources between the two. If this still doesn't make much sense, let's just take an example. Let's say that the first person had 0.95% of that, and then the other person had 0.05. Well, if we multiply them together, then we get some very low value. But then if they are more balanced, like if both of them got equal amounts, 0.5 and 0.5 respectively, then 0.5 times 0.5 equals 0.25. As you can see, this is much, much higher. So it's basically like saying the more balanced this is, the higher the derivative is. The more fair it is, basically. And connecting this back to the derivative, we can see that this is precisely like this. If the output of the sigmoid is 0.5, then 1 minus 0.5 is still 0.5. So that would be very balanced. But if it was very low or very high, then the derivative would be small. But let's take that most balanced case one more time. If we have that most balanced case, then as we discussed, that yields a derivative of 0.25, right? Turns out, as we discussed, 0.5 output of sigmoid means that the z is 0, that the input of the sigmoid is 0. And it turns out that the derivative is the highest here. When we have the highest derivative or the maximum derivative, it's formally called the Lipschitz constant of a function. It's like the speed limit of the function, in a way that we can say that it's like a cap on the derivative, like the maximum it can go, basically. And in this moment, we can see that as it goes more and more to the left and more to the right, because we're becoming more and more confident about our decisions, we have a smaller and smaller derivative. So what can we say about this? If the wave vector is orthogonal to the input vector, then we are at a decision boundary, which is like the border of two decisions. It's also the state of maximum entropy or uncertainty. As we just discussed by analyzing sigmoid's derivative, we discovered that also at this point, the derivative is also the highest. And so it's like the most change. This is called its Lipschitz constant. As we become more and more confident, as those probabilities go towards 1 or go towards 0, and then the derivative decreases because we're becoming increasingly more sure about our decision.